Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me is...
I'm Robert Moore.
This is episode number 23, season 3. We're broadcasting live from University of North Dakota. We have a brand new setup, so it took us a few minutes to
Took us a few minutes to work everything out.
Yeah, so that you'll notice the cameras look different. They're much wider field of view than what we're normally used to it. I think they're higher definition, so maybe we'll get a better view for people. So we'll see how things go. If you can't hear us, or if you notice some issues, please let us know in the chat. We do have a chat feature that's running, so if you have any questions or comments that you'd like to make throughout the podcast today, please feel free to use that. Okay, so Robert,
Yeah.
start with the disclaimer.
All right. Our disclaimer, as usual, is that the opinions and so forth that are expressed are those of myself and Wayne. They are not the opinions of the University of North Dakota or the Department of Physics and Astrophysics or the College of Arts and Sciences. It's just us, folks. We're winging it here.
And we weren't here last week. Do you want to say a little bit what happened there?
I will. That was my fault entirely. I apologize for that, folks, but I've been having some back trouble, and we got to just before time to come down to start the podcast, and I realized that without grunting, wincing, and groaning and complaining, there was no way I was making it through an hour sitting here. So...
And you feel a lot better today.
I feel a lot better today.
So you're on the mend for sure.
Oh, yeah. It's still there, but...
Not as bad. You can bear it, right?
I can bear it today.
That's good. As Adam said to Eve, bear with me.
Wow. Rawr.
So we're going to start off by doing some updates. How's that?
Sounds
some of
good.
the news items that we've covered in the past. So let's start maybe with the first one.
So let's start with the first one. Yeah, Corona Borealis. It still hasn't kicked off.
We've been waiting for like a year now. You realize that?
It has been a year, hasn't it? Mm-hmm. But I was going to ask you earlier when we were kind of looking at these things, is this a situation like the sunspot cycle where it's, 11 years or 13 years?
It's 80 years.
Okay, so it's 80 years, but it's plus or minus.
Yeah,
what,
there's always an uncertainty.
5
right?
years, something.
Yeah, that's the problem, right? People will come up with, it should go off July of 2024.
Right.
And here it's like a year, 12 months later, so it hasn't gone off yet. It's like, okay, there's an uncertainty there. Maybe it's like plus or minus a couple of years or something.
Right.
But, keep looking. It reminds me of when astronomers made predictions. They don't do it so much nowadays because they learned their lesson. But they made predictions about comets.
Right.
Comet so-and-so will go by, and it'll be like the brightest, like at its brightest, it'll be like, as bright as the full moon. And then it turns out to be like this dud, right?
One of the ones I remember that happening to most recently is Comet Holmes. If you remember back in 2009, 2010-ish, and they were like, it's going to get bright. And it did. It got brighter and brighter and brighter. And then all of a sudden just went poof and disappeared. And when you look at it through a telescope, it was real easy to see why. It just basically disintegrated.
Yeah. That happens a lot too. But a lot of times these things are unpredictable. That's the issue.
Right.
Not everything in science is predictable. We always have to remember that.
There you go.
So just to give, in case people are not aware of this star and what's supposed to happen. So first of all, the constellation is on the right. So it's out for Corona Borealis, the northern crown. So it looks like a crown. You can't see it from the suburbs.
Oh, no, it's a dim constellation.
Yeah, it's a dim constellation, and you have to be out in the rural area. So I was able to look. I was in a dark site a couple weeks back, and I was able to see it quite easily. But yeah, you have to be somewhere where there's not a lot of light pollution. And the star that we're looking at, if you look on the right, there's sort of on the bottom left of the right-hand drawing, you see the label T, and it points to a certain star. So that's the star that we're interested in keeping an eye on. And what it consists of, which you see on the artist drawing on the left side, is a white dwarf that's in orbit around the center of mass of a red giant. Mm-hmm. And a white dwarf is the end state of a low-mass star. And by that I mean any star that has a mass of about 8 times the mass of our sun and smaller than that value when what we call a main sequence star. This is the phase in a star's life where it's converting hydrogen to helium in its core. It represents about 90% of the total lifetime of a star.
Right.
So, and that's because that's the longest, slowest burning stage in terms of nuclear fusion that a star will undergo.
Right. All the other stages of fusion flash. If I
Yeah, or
remember
much
correctly.
faster.
Yeah,
and as
they
you get
burn through real quick.
right, and if you talk about high mass stars that burn through heavier and heavier elements, as you go up the sort of periodic table of
Yeah.
elements, the time scale gets shorter and shorter and shorter
Yeah.
until eventually you reach the end where essentially everything is happening within like a second or two. So it's that short. So for a star like our own sun, for example, it'll be in this phase of being a main sequence star for about 10 billion years in total. And we're about 4.5 billion years into that now. So we have roughly 5.5 billion, so roughly halfway to go before the sun evolves off the main sequence.
Right.
So the white dwarfs are the end states of these low mass stars. So clearly, a star like this, nothing would happen to it if the white dwarf is completely isolated. And what holds up, if you like, the star from collapsing in on itself is what we call electron pressure. So essentially the matter gets squeezed to such a huge extreme that it takes on this new form of matter, a new state of matter that we call degenerate matter. And it's really the fact that the electrons don't like to be inside each other.
Right.
That you can jam them close together. It's like I like to use the analogy of pouring marbles in a glass vase or a jar. You can put so many marbles in there and that's it. You try to stick that extra marble in there and push down on it with all the strength you have, and you might split the side of the container because the marbles won't get any closer than a certain spacing.
And there are objects that do that equivalent, and they formed in neutron stars or black holes.
Mm-hmm.
Yeah.
So the electron pressure prevents the white dwarf from collapsing on itself. So normally it would just stay there, sort of a stagnant object, just cooling down to the background temperature of outer space. Now, in this situation, we don't have an isolated white dwarf. We have one that's a binary star system. So two stars in this case in orbit around their center of mass. And what has happened here is that the other star, the one that is not a white dwarf, it has a smaller mass. So if it formed at the same time as the white dwarf star, because it has a lower mass, it takes much longer to go through its different cycles of its life. And so it's finally reaching the point where it's evolved off the main sequence and is now swelling up to become what we call a red giant. So the white dwarf would have already went through this phase earlier on. And what happens in this case is the star swells up in size and can get large enough, as you see in the drawing, that some of the material in the outer envelope of the red giant actually feels a stronger gravitational pull towards the white dwarf than it does to itself. And so the white dwarf can literally strip off some of that outer material.
Do we want to get into Roche lobes and all that? No, no.
We can later. We have a lot to talk about today. So.
True.
And the thing is, because the white dwarf and the red giant are in orbit around each other, the material doesn't fall straight towards the white dwarf. It spirals in this what we call an accretion disk. Mm-hmm. And it's like analogy would be if you pull the plug in your bathtub and watch the water go down. It doesn't all go down straight into the drain. It usually spirals around. Okay. So what happens is that material has to go somewhere that's in the accretion disk, and eventually it'll fall on top of the white dwarf, building up its mass. And what happens is that material becomes highly compressed. It's mainly made up of hydrogen. Mm-hmm. And it'll reach the point where it actually ignites through thermonuclear fusion, hydrogen into helium. And what happens in that time is when the onset of that hydrogen fusion occurs on the surface of the white dwarf, is you get a sudden brightening, of course, of the star itself. Now, if the mass of the white dwarf is significantly below about 1.4 times the mass of our sun,
right,
that material would just be converted into helium, and then it's like pouring gasoline on a bonfire. You get this flaming up that occurs, then the gas gets consumed, and then the fire goes back down to the original brightness that it had just prior to putting the gas on the fire. Same kind of thing happens here. The white dwarf will flare up, become bright for a period of time, depending on the exact situation, let's say a week or so. Mm-hmm. And then over a course of several days after that, it will fade and fade. If you have a large enough telescope, you could watch it fading away probably for a month or so. And eventually it'll go back down to the original brightness before it flared up. And we call that a nova. Nova means new. And it just comes from the fact that there'll be a star in the sky, let's say if you're in a dark location, and you can't see that star, it's too faint. But then when it goes nova, it can brighten significantly, and all of a sudden you see the appearance of a new star, a nova. Now, we can discriminate between those and another type of object that has the word nova in it, and that's the supernova. And that's a different type of beast altogether. These are stars that explode, and they increase in brightness way more than a typical nova. So
Right.
intrinsically, they get really, really bright for a brief period of time.
Their intrinsic brightness is higher than that of the galaxy they're part
Well,
of.
here's
correct?
yeah, and you can here's this way. You take all the light that the sun will output in its 10 billion year lifetime, multiply that by 100, and release it in 1 second. That's a supernova.
There we go.
So it gives you an idea of how much energy is released in one of these events. So what happens in this case is for the T Corboreal star, we have a recurrent nova, which means that as that material gets used up and it brightens for a period of time, then dies out, then material still gets transferred from the nearby companion star over time, builds up on the surface of the white dwarf, and then it flares again. It would be like someone periodically dumps gas on the bonfire. You get this flaring up every so often. Now, in the past, we've recorded the nova event a couple different times. We look in the historical records. That's another reason why we want to keep records of what goes on in the sky. You never know when it becomes very useful. And we discovered from the analysis of the flaring up and the time between the nova events is roughly on the order of 80 years,
Okay.
which would put the event occurring in the summer of 2024. Didn't happen, but of course, there's always an uncertainty on that. It's not going to be an exact type of thing. And so it could be 81 years this time around.
Right.
Or maybe
Which it
80
has been now.
Yeah, or maybe it's 82 years.
Right.
These kind of things. So for those of you who are looking and are watching and have been keeping an eye out on the news for this thing to go up, it will get as bright, we predict, as the North Star when it does go. Now, the North Star is not the brightest star in the sky from the Northern
It's
Hemisphere.
not really even a bright star, to be honest.
No, if you're into magnitudes, it's about second magnitude, which means it's bright enough. You can see the North Star even from the city. If you know where to look, you can see it. So it'll get bright enough you can easily see it with the unaided eye, put it that way.
Right.
And so you'll be able to tell when the event happens. You look to this area of the constellation. If you see the presence of a new star, then clearly it must have went off. And of course, it'll be all over the astronomy news and so on. And so we'll see. Now, there has been a prediction, a more recent prediction of when the eruption will occur, when the star will go nova. And here's a research note that was published by John Schneider. This was back in October last year. And he makes actually two predictions based on the analysis of the past light variation of this object. The first date we've already passed. It's around March the 27th of this year.
Okay.
The second prediction in this research note is November 10th. So that obviously hasn't come here yet. We're waiting for that. So maybe by November, this thing will go off. But then notice at the end, it says, or later.
Or later.
That's a very safe prediction because
Yeah,
you know
yeah.
it's going to happen at some point.
It's going to happen later.
Yeah.
Yeah.
So we'll see if this person is correct or not. If it does happen around November, then notice that even for him, it's imprecise. It's either in March, November, or later. That's not very,
Right.
you know. And that's because of the different periodicities. You do the analysis of what we call the light curve, the variation in the brightness of the object over time. And you can do some fancy mathematical analysis, Fourier type analysis, looking for periods. And some of the stuff pops out that one period would have it come back in March of this year. Another one would be November. And there are probably other ones that would occur later.
Right.
So that's kind of what's happening
Higher
here.
order analyses.
Yeah.
And
Well, the last
so
time it
forth.
occurred was what? Just after the Second World War.
Okay.
Was the last time this star went nova. So we expect it to occur. Of course, there can be an eruption, a disruption in the fuel supply. The transfer could have slowed down more significantly. So it could be like 10,000 years from now. We're just based on what has happened in the past, projecting forward in time to see what's going to happen
Oh, that's
next.
a good point. I hadn't thought about that. If that companion star is really passing through the giant phase now, all of its outer envelope may have been stripped off and in the accretion disk or something, or it may be going more tenuously.
Well, here's the thing. If you could monitor the size of a red giant
Yeah.
every day, how do you know it doesn't undulate, doesn't fluctuate?
Well, the ones we do know about do undulate.
Because we know they fluctuate over, or there's changes that happen over long time scales,
Right.
thousands of years. But on the order of 80 years, how do you know there's not like a swelling outwards and then a decrease and then a swelling and a In fact, we see a lot of stuff that we didn't know about when we'll talk about it a little bit later here, like Betelgeuse and the great dimming that started in 2019 through 2020 and so on. I mean, that was a big surprise to a lot of people. So
Right.
clearly there's things that we don't know, right?
But they
And
point to
details.
things, and people start going, maybe we need to poke at this a little more.
Yeah.
Maybe we do need to understand what's going on here.
So the moral of the story here is what? Keep looking up.
Keep looking up.
That's what you got to say. Now, the other update is the very interesting object that was discovered not that long ago, a few weeks back, and this is the 3I Atlas. This is this interstellar comet that's inbound. It's going to make its closest approach to the sun in October of this year. It's still going to be fairly far away from the sun. It's around the orbit of Mars or so, roughly.
Right.
It's not going to come near the Earth. In fact, as the comet reaches the close approach to the sun, we're actually on the opposite side of the sun. So it's going to make, viewing with a telescope impossible, at least for a few weeks, until we manage to move in our orbit, and the comet is moving, of course. So the alignment is such that we don't have to look directly towards the sun to see it.
Right.
And
So it's never going to get that bright or that high in the northern sky for us.
not really.
Yeah.
Yeah. So it'd be nice to see if we get some of the rovers on Mars be able to take an image of it in the sky.
Oh, that would be neat.
Because
Yeah.
they have done images of Aurora. They've done images of the
Earth.
Phobos and Deimos, the two moons of Mars. So they might be able to capture, the comet. Who knows? We'll see
Who
how
knows?
that all lines up. But here's the sort of an image that was taken fairly recently by the Gemini North telescope. So this is on Mauna Kea in Hawaii. This is an 8-meter class telescope, so it's not a small telescope that you would buy off of Amazon. This is a fairly large telescope. You can see from the image that you can see the cloud or fuzziness around it. That's the coma. So that would tell you this is definitely a comet-like object. It's
Right.
not an asteroid because you wouldn't expect to have this normally. And one of the things, there's been a few reports I noticed of people doing images and trying to understand what is the chemical elements that the object consists of. So doing spectroscopy, as we would say. And there's not been any real firm detection of different molecules like you would expect that normal comets would have.
Huh.
So
Now that's interesting.
yeah, so I'm not sure what's going on here. Is it like the volatiles that would be evaporated off the surface is still too far away from the sun for that to occur, or what the issue is? There's also, of course, a very small selected group of
Oh, Lord.
quote-unquote scientists that have speculated that this is an interstellar spacecraft of alien technology, and that's like you jump to like the most the chance of something not being the truth. You jump there first before the obvious thing that this is just a comet. Looks like a comet, smells like a comet,
It's probably a comet.
and
Come
yet it's a UFO, like alien UFO flying. So
Aliens.
it's like, oh my God, it's like, we can do better than that, I think.
I would think so, too.
So
Yeah.
we're going to keep an eye on this object, of course. So hopefully we'll have some better views.
For as long as we can.
Yeah, and we'll get close enough that people will be able to get some good measurements of the chemical composition, and that's the interesting thing.
That's the interesting thing.
I mean, you like to look at the different isotope ratios and stuff because we'd expect that could vary from location in the Milky Way to location in the Milky Way. And
I got to be honest. I like seeing what kind of organic compounds start coming out. Fullerenes, benzenes.
well, there's even been amino
acids,
yeah.
things like that. What comes out of these things? Because to me, there is still an open-ended question of panspermia. I hate bringing that one up too, but it's a legitimate concern. A legitimate question. Did the building blocks for life come to our solar system from other parts of the galaxy?
Yeah, and one of the things that people look for is the handedness of the different types of important molecules, and the ones that life forms from is right-handed. Of course, what you call right or left, it doesn't matter. It's just one sign, one sense, if you like clockwise versus counterclockwise.
Right.
And if we find molecules that are left-handed, right, so it's a chirality
problem.
property, right?
Right.
Then that would tell you that's not from the Earth if you get this left-handed stuff. And if we find evidence of that somewhere, whether it's here or not, that would be extremely interesting.
Absolutely.
The other thing people like to understand is where did it come from? So can you, as an astronomer, can you trace its path backwards in time to tell me what star did this
It might
object
have come
originate?
from.
And
Yeah.
you can't tell. You can't tell because it could come from anywhere almost in the lower part of the disk of the Milky Way, probably, right?
Right.
If it came from out in the halo, it would have a different speed.
And trajectory.
and trajectory. So we think it came from what we call the thick disk part of the Milky Way. But you can never truly trace back where's the originating star, if it even formed
Around a star.
Maybe it came from an interstellar matter, a nebula
Right.
or something, right? Who knows? But anyway, so that kind of stuff, unless it says like made in,
Made in Delta Quadrant.
yeah, epsilon, zeta reticuli, right? That's the
Zeta
one that they always
reticuli,
mention.
Epsilon Eridani.
Yeah, chances are we're not going to know unless it has unique composition. We're somehow able to type the host star or location that has the exact same spectroscopic composition. It'd be hard pressed to be able to tell where it came from exactly.
Absolutely.
Unfortunately.
So, yeah.
Now
Here's
the
the fun one.
Yeah, here's the other interesting that just came out. So we had to make sure that we mentioned on today's podcast. And this is the final proof that Betelgeuse, just don't say it 3 times in a row, Robert,
I will make sure not to.
which is the red giant, super red giant that we find in the constellation Orion. So Orion is the one that you see on the right panel. That is a winter constellation for us here in the north. Of course, there's a summer one in the south. And of course, if you're in the south, it's upside down from the view that you see here.
Yep.
So we're being northern hemisphere centric here. So you can see Betelgeuse that's labeled. So it's the brightest star usually in that constellation.
Armpit of the Great One.
Now, that star went through the Great Dimming back in
Right.
2019, where it actually was no longer the brightest star in the constellation for a period of time. And it was interesting. I remember looking at it, you could easily tell the difference.
Yes.
You could compare its brightness to the other stars of the constellation and tell it wasn't the
I
brightest.
hadn't been watching it, but I looked up during that time period and was like, whoa, Betelgeuse is a dull red, not a bright red anymore. It was noticeable dimming.
And after a period of time, it did get brighter. And now it's essentially back to its original brightness again.
Yep.
And we think it's due to the fact that the star had a big outburst of dust. So there was like a dust cloud heading more or less towards us. And that would block and scatter the light coming from the star itself. So it would cause its overall brightness to go down for a period of time until that cloud, gets
Right.
away, dissipates.
Kind
and
of
so
like
on.
what a cloud does when it grows in front of our sun,
Yeah, well, just think here when you
Dims
get a
it
lot
for
of
a while.
smoke in the sky and you're trying to see the stars at night.
Right.
Same
And-
kind of effect in that sense. So when people have monitored the brightness variation in Betelgeuse, of course, when this event happened in 2019, Betelgeuse is at the end of its life. It's a high mass star, so we'd expect it will go supernova, one of these core collapse supernova. So some people speculated that it was going to happen very soon, that this was a sign of the beginning of the collapse of the star to ultimately go supernova type 2. That didn't happen. And obviously, or you would have heard about it, and we would have said something on the podcast. By now,
Absolutely.
and
We
then
would have told you
Betelgeuse
where to go
wouldn't
out
be
and look
there
at
by
it
now.
because it should be visible in the daytime sky when it
for a
happens.
period of time, yeah.
Yeah.
Assuming the constellations in the daytime sky, which it is
Right.
right now, this time of the year in the
Yeah.
summer. Now, one of the things that people looked at was very carefully the light changes that the star had gone in the past. And it's interesting that there is a lot of period of changes of brightness of the star. Some period changes on the order of every 6 years. It goes through this sort of periodic change in brightness. And then there are other type of periods superimposed on that. And the 6-year period was interesting because some astronomers had speculated that that's what you'd get if there was actually a companion star in orbit around Betelgeuse. So a period of time it would be in front of the star, blocking the light, and then it would be in behind, and then reducing the overall light of the system, and so on and so forth. And so that was a speculation. Well, now we have direct observation. This is the exciting news. That's the image that we see there on the right-hand side.
On the left?
The left-hand side. The object on the right is Betelgeuse. That's sort of color-coded. You can see the white in the middle and the kind of yellowish and browns on the outside. But that blue sort of extended object you see that's on the left then
Yeah.
is the companion to Betelgeuse.
And
So these are-
notice you say companion because it's not actually a star.
Right. So this is also taken from the Gemini North telescope again. And scientists, and there was a couple papers that were published recently, which we'll see in the next slide here in a second, but scientists estimate that companion star has a mass of about 1.5 times our sun's mass. So we classify it as a low mass star. But they also speculate that it seems to have the properties you would expect of a star before it reached the main sequence.
Right.
So it'd be a so-called pre-main sequence star. So this is before the temperature in the core of the star has exceeded 10 million Kelvin to allow fusion of hydrogen and helium to occur,
Right.
which we would signify as the main sequence phase of a star's life.
And it kind of shows some of that stellar evolution we've hinted at and discussed before, that low mass star has not even become a star yet, while Betelgeuse is nearing the end of its life. Betelgeuse is what, about 30, 40 times the sun's mass?
Yeah, it's a lot more mass.
So its life extends over a few million years, a few tens of millions of years, whereas this 1.5 would have been a few billion years.
Right.
And it doesn't even get to kick off before Betelgeuse is going to explode.
Yeah, and the other thing is would you really expect, I mean, it's an assumption you can make that these two objects formed at exactly the same time.
Right.
There can be a bit of a delay in formation. That would be enough.
But over the,
Right.
10 million years, though, is a blink of an eye astronomically and geologically.
But not for a
speaking.
high mass star like
But not for a
Betelgeuse.
high mass star.
Yeah, then time scales are important when you're talking about millions of years. The other thing that's interesting is the separation of the two stars. Assuming you got the distance to Betelgeuse, it's on the order of 500 light years or so. It's hard to measure. It turns out, like Gaia, which measures the distance of stars, nearby ones using the parallax technique, it's hard for Gaia to have measured the star because it's just so bright.
It's too bright. Yeah.
So you almost need like a smaller telescope in space to do this type of measurement.
It's so bright. The bottom line is it's hard to say, okay, it's on this pixel.
Yeah,
which is what you need
center.
to be able to say, hey, this is its position.
Right.
You need to know that one pixel it is on.
Yeah.
Because stars, see, at the distances they are, they're one pixel, except for ours.
Yeah, so Betelgeuse would be saturated in detectors, of Gaia that would use normally the setup for measuring much fainter stars. We'll get it eventually. We'll just use up a
absolutely.
different detector for bright stars.
Right.
We'll have to do that.
Would speckle work? Speckle
I don't know.
interferometry?
Yeah, because a very short exposure, and you can also, you don't want to defocus because you want as sharp as possible.
Right.
But you can design. I'm sure you can design like nano satellites, these micro satellites.
Oh, true. Yeah,
go up
with
there and
very small aperture.
Yeah, and then very high resolution cameras.
Yeah.
Very small pixels, and you're in space, so you don't have to worry about the atmosphere. You should be able to get a decent, parallax measurement of stars like
See,
this.
we need to design missions and find us a launch platform.
Yeah, we should write a proposal to do this.
Absolutely.
Now, the separation of the two objects here, given the estimate of the distance to Betelgeuse, puts it at about 4 AU. So you remember what an AU is, Robert?
Yeah, that's the distance, the mean distance from Earth to the sun.
So this is about 4 times the distance of the Earth to the Sun away from Betelgeuse proper. So it's fairly close.
It's
not that
it's
far. but-
pretty. Yeah, that's really close. That puts it well inside the envelope of a supergiant.
Yeah, for sure.
So
when-
that's the other problem is
Right.
it's inside Betelgeuse.
So
Essentially.
what happens when Betelgeuse eventually explodes, which it will?
This thing's probably going to evaporate. It's probably going to just be blown off with the shell of Betelgeuse.
Yeah, so it'll be destroyed, unfortunately.
Yep.
Anyways, here are the 2 research papers that were published recently that describes the observation of the companion to Betelgeuse. So if you're into that and you would like to explore further details of the observations in this system, here's where you'd go.
I'm going to comment, though. One was in December of 2024. One was in January of 2025. Why did it take so long to pick up on the popular side on this then? I mean, that's 7 months.
Yeah, I mean, this is when it gets published, right? So you want the stuff
Right.
gets peer reviewed first, and then you make it public.
Okay.
You got that kind of stuff. But yeah, it took a while for this to come out in the news. The recent observations are made by Gemini North, so I think they got good data.
Okay.
So I think that's its new observations taken with a new instrument. I can't pronounce the name; it's an Hawaii name.
Oh,
It's
right.
APO something something something.
Yeah.
But anyways, I think
No,
that's
no
the new
offense to
data.
any Hawaiian viewers,
No.
but
Yeah,
I
it's just
have
my.
problems pronouncing with my
I've never heard it
American English
pronounced, so
tongue.
I'm not sure what the pronunciation
go.
is. But it's a new instrument on the Gemini North, and that's where the new data
Okay.
comes from. So, anyways.
All right.
Now, talking about suns,
Yeah.
So the Parker Solar Probe, which is an orbit around the sun, so it was launched way back in like when was that launched? 2018 or
2018,
something
something like that.
Yeah. And so its goal is to take detailed observations of the sun as close as possible, way closer to any other spacecraft have done in the past.
Right.
And one of the closest approach that it made was on Christmas of last year. Mm-hmm. And they're still analyzing the data, and some of it was released recently, last couple of weeks. So the image that you see, first of all, the image on the right is of the Parker Solar Probe before it was launched. So you get kind of an idea of what it would look like. Of course, it unfolds when it gets out there. But a lot of the stuff the interesting thing about this is that it's tucked behind the sun shield, which is on the very top. And that's the part of the spacecraft that's pointed directly at the sun.
Okay.
And you want that sun shield to protect the instruments or they're going to burn up and melt. Mm-hmm. And the idea is if to sample something, you stick sort of a probe out the side a little bit and measure things right directly that way. They kind of get on the edge of the protection of the sun shield.
Right.
Without, you can think of a little bit of antenna sticking out and also it melts away, right? Because you're out too far, right?
Right.
So you got to be very careful. Now, the image that you see on the left, and you can see the direction of the sun, that's why you don't see direct pictures of the sun.
Right.
Right.
It can't. The instruments
Yeah.
would be just blown away.
Right, because we're just way too close. So how close? Well, in December, the spacecraft came within 3.8 million miles of the sun. And that's the closest that we've ever gotten to the sun. And so I got any measurements, including the picture you see on the left. Now, if you go online and look for this, you'll see actually a little movie clip that they have that they can see all of the solar wind, which you see here, changing. It's very, very dynamic. But yeah, it's interesting that this is what, if you want to know the detailed structure of the solar wind and when coronal mass ejections occur, these eruptions on the surface of the sun, having a detector that close to the sun to resolve these details is extremely valuable.
Right. I'm looking at all the high end. Those little spots, by the way, are probably not stars.
Cosmic rays. Yeah.
Those are cosmic rays and solar wind particles.
And even bad pixels.
Smacking the crap.
Yeah, and I'm sure the detector degrades over time, too.
Yeah.
Now, there's supposed to be another close passage coming soon in the fall around this. They say, if you want to go to the sun and take detailed measurements, why don't you just go at night, Robert?
I don't know. I was going to mention something about that. You beat me to it. But I'm also going to mention that aren't they hoping they can get down to 1.6 million miles?
Yeah, they're going to go a lot closer
before it finally goes kaput.
Yeah, that's the hope. So you don't want to do that right away because you want to be able to get some measurements from it. Oops, it melted. That's the end of the probe, right?
Right. You don't want to do that right off the bat.
So you go on these sort of highly elliptical shaped orbits to get ever so closer and closer.
Right. And the other thing that amazes me about this, they had to burn as much rocket fuel as if they were going to the outer solar system, because what people forget is angular momentum. And the Earth is going around the sun at a certain speed, so any probe is going to have that velocity around the sun too, and you've got to burn off all that speed so that you can fall into the sun. And that takes just an inordinate amount of fuel.
Yeah, for sure. Yeah, that's why it's hard to get to Mercury. Mm-hmm. In fact, notice that we have like different probes, like the one that the Europeans sent.
The
Bopo,
something like that. We sent Messenger.
Yes, that they do a lot of loops around the planets, like around Venus, around Earth, back again.
They got to kill the speed.
It's no direct route for sure. You don't have a powerful enough rocket, and it costs too much. You have to put up so little mass you couldn't afford.
Right.
A massive spacecraft is.
It's crazy.
Yeah.
You think about it, you just launch it and let it fall to the sun. No, you've got to bleed off all that speed, and then it picks up speed going in towards the sun, and you got to bleed off all that speed.
Yeah, it's very difficult. So, but it's amazing that we can do that.
Yeah.
With
it just takes a lot of math, folks.
Yeah.
A lot of math.
For sure. Okay, the next story I want to mention here was in the news a couple of weeks ago, and this is we talked about supernova already today. Mm-hmm. So this is the case of a white dwarf that exploded. So carbon detonation supernova, the so-called Type 1a supernova.
Type 1a, yeah.
And so you have the same situation in T-Core Bohr if you were able to have enough mass accumulate on the surface of the white dwarf so it pushes its mass over the limit of about 1.4 solar masses, then the electron pressure couldn't support that weight, if you like.
Then you squeeze that one extra marble into the vase.
Yeah, and then you collapse in on itself, and the whole thing blows up. And since white dwarfs are mainly made up of carbon, we call that a carbon detonation supernova. Now, in this situation, this is a star that has exploded twice, has gone supernova
Right,
twice. And it's like, at first
seems-
thought, it's like, how can that happen? Like, that doesn't make sense. But here, it's a little bit of a trick in this sense, right? A little bit of a
Is it that it blew up and then stuff fell back onto it?
Yeah.
And shockwave. Okay.
Yes, that's what's happening.
Okay.
So first of all, the image on the left is taken by, or the image, there's only one here, taken by the Very Large Telescope, which is one of 4 telescopes that's operating, the VLTs, there's 4 of them, there are a lot more telescopes, operating in Chile, so it's by the European Southern Observatory. And you see an image taken of what we call a supernova remnant. So the leftover many years after the star had exploded. Now, you see the color coding, so people recently have done detailed analysis of the supernova remnant. And if you look very carefully at sort of, that would be what, the 10, 11 o'clock position. So that would be on the left, the upper left of the supernova remnant. And in fact, looking at the blue part, looks like there's 2 layers, like 2 double shells.
Mm-hmm.
So that's the interesting layer of calcium-15. So it's 2 layers of calcium-15. Now, on the outside of that is a single layer, that's sort of the yellowish orange light, of sulfur-12. Now,
And I'm impressed by those designations anyway, because that means the calcium has been ionized 14 times.
yeah,
And the sulfur has been ionized
11 times.
11 electrons stripped from it.
Yeah.
14 from that calcium.
Yeah.
Holy, the energies needed to do that. Holy cow.
And since the sulfur, that is that yellowish orange color, is on the outer part of the supernova remnant, whatever caused it happened first, because the whole thing's expanding outwards.
Mm-hmm.
The blue part, which is the calcium double layer, that happened after, because it's closer to the center,
And that makes sense.
right? Because they
It's
travel at a
travel
certain
time.
speed, and if you've been traveling longer, you're going to get further away from
Absolutely.
your destination, right? From the place that you started from, that is. Okay, so what we think happened here is that the sulfur was actually produced when there was a helium explosion at the base, or the outer, sort of the base of the star itself, the outer envelope, right?
Okay.
Put it that way. And then that created, so that's the first supernova event.
Mm-hmm.
That created shock waves which propagate outwards, but there's also a reverse shock that can occur.
Okay.
And that reverse shock then squeezed the material in the core of this white dwarf, mainly made up of carbon and some oxygen, and that initiated the collapse into this carbon detonation supernova, the type 1A. That's the second explosion.
Okay.
So it's a double supernova.
It's a double tap. Pop, pop.
Yeah.
And that's probably actually how it did. Is there was an initial pulse and then that compression and then boom.
So you wonder, well,
second
how
wave.
can that be? Well, people have modeled this. This is nothing new. So here's a modeling done by the University of Tokyo. And what you see here on the outside is a disk. Okay, so instead of the sulfur layer, so we have a disk of material, and that disk of material piles on, and you get that initial
Boom.
boom, explosion. And then the reverse shock causes the interior part of the star to collapse in on itself to go the standard carbon detonation supernova, the type 1A.
Okay.
And
Because
then
that
that blows
initial
outward.
shock wave would push faster.
Yeah, it was compressed
And
the
compress
material.
the material
Yes,
behind it.
Yes.
Yep. Okay.
So then you get the double detonation that's occurring.
I can
here.
buy that for $1.
So it looks, I mean, a lot of stuff was simulated, as I said in the past, but there's no clear evidence that it happens in nature. And just because you simulate something or you calculate something,
You got to see it first.
it doesn't mean that Mother Nature obeys by what you're seeing, right? Or what you calculated.
In my
So-
geology background, we talked about this. For there's something to be a mineral, you can't produce it in the lab and name it. For it to be a named mineral, you have to find it in nature. So we can take stuff we know the Earth is made out of, squeeze it to the pressures we know are going to be in the interior of Earth. And we found, crystals forming out of it that would suggest, hey, this mineral should show up. And one of those that happened recently, fairly recently, is a mineral called bridgmanite. It was hypothesized because it was produced in the lab, but there was no evidence for it from nature until a spot of it was found inside of a meteorite.
Oh, interesting.
And then they could name it, and they named it bridgmanite.
Oh, cool.
And it's a post-perovskite mineral.
Yeah. Or you have the reverse, right? You find something.
And then go produce it in the lab.
And then go see if it makes sense, right? How
Right.
this exists to begin with.
Absolutely. That's been done quite often.
Yeah. So they go hand in hand. That's why you got to have, it's almost like the argument of observation or experimentation with theory.
Mm-hmm.
And sometimes we joke they're theorists in physics, they're experimentalists in physics. And you joke, well, which one do you need? Some people would say, well, theorists can do all kinds of stuff as long as they stay within the natural bounds of what's allowed from a physics and mathematical point of view.
But how do you know that until you've observed it?
And then the experimentalists would say that we constrain the theorists.
Mm-hmm.
We don't let them go wild with all their speculation.
Right.
We actually show what's actually out there and what's possible, so narrow down the models.
And sometimes they constrain themselves because they know that there's some more physics to find because the math says there's a singularity. But, in reality, is there really a geometric point of infinite mass out there? Or infinite density, I suppose I should say.
Well, I mean, that's just where the general relativity breaks down. And we
Right.
know it has to break down at that situation, right?
There you go.
And I'm thinking more of like in 1998 with the observational discovery of dark energy. And prior to that, theorists would have said, okay, because way back in Einstein's day, right?
Right.
There can be this,
Cosmological
anti-gravity type of thing where the universe is accelerating its expansion. But there was no justification why no motivation behind that
Right.
based on the current observations prior to 1998. So it's there, theoretically, but it didn't seem to match nature.
Nature.
And
There you
then,
go.
of course, when it's observed, then, of course, right
Now
away.
all of a sudden, okay, now we can
Oh,
talk
yeah, it
about
looks like there's something there, right?
And we're going to give it a name, but we don't know what it is really. So what do we name it?
Yeah.
All right.
And the other thing that popped up recently is the announcement of the discovery of the most massive black hole merger that has been detected. And this is with gravitational waves. So this actually happened, the event itself occurred way back in 2023. And so November 23rd. And it was detected. So we get a little bit into what's going on here. We've talked about gravitational waves, of course, on other podcasts. So it's one of the predictions from the Einstein's theory of general relativity that if you have accelerating masses, that some of that energy in the system goes into shaking, essentially, space-time. It causes a stretching in one dimension and a squeezing in the other. And that this disturbance can propagate at the speed of light from the object that's creating the disturbance itself. And of course, it gets weaker with time. Its amplitude falls off as 1 over the distance.
Okay.
So unless there's some kind of thing happening that creates gravitational waves near the Earth, it's going to be very hard to detect them. Most sources are probably going to be tens of millions to billions of light years away. So by the time the gravitational wave reaches the Earth, it's very, very, very subtle. It's almost like if you're, I don't know, on a boat in a large lake somewhere, and let's say you're fishing, and the water's extremely calm, and somebody on the shore throws a pebble in the lake.
Right.
Those waves emanate outwards in all different directions on the surface of the water, of the lake. Eventually, those waves will hit you, but by the time they hit you, because you're far away, the amplitude of those waves is so minute, you're probably not even going to notice it.
Right. You probably didn't see it, feel it, anything.
Nothing. So that's the same kind of thing here. The challenge has always been for many years now is how do you measure something that's so subtle like that? Very, very difficult. And when we talk about the average sort of stretching and squeezing of space, it's like the fraction of the radius of a proton type of thing.
Right.
Well, of course, you never say never, and especially in science.
Right.
And experimentalists, people are very, very clever. So experimentalists have finally cracked the nut on this back in 2015.
Right.
They discovered the first detection of the first gravitational wave, which was from the merging of two black holes. So there are situations where we have black holes, like we've seen with T-Core Bohr, where there's two objects in orbit around each other. If both of them are very high mass, they can ultimately go supernova and collapse down to form black holes. So you then have a system where there's two black holes in orbit around the center of mass. And with the release of gravitational waves, that takes energy out of the system, and that causes the separation distance of the two black holes to become shorter. So they get closer and closer together over time. And eventually what will happen...
And the closer they get, the faster it happens, because the more energy they're dissipating, and eventually they cross over and they merge.
And in that merging process, you get a burst of these gravitational waves.
Right.
And if we have a detector that's running here on Earth at the time, when they reach us, which could take a long time, right? If these systems are like 1.5 billion light years away, we have to wait 1.5 billion years for that disturbance to reach us, traveling at the speed of light.
Right.
But there's these things in the universe, these like merging black holes and so on, that are probably occurring every once in a while and have been going on for billions and billions and billions of years. So there's been enough time to have elapsed for the gravitational waves to be washing over the Earth now.
Right.
You just have to have this sensitive enough equipment to detect them. And we do now, at least for some of them. And so since then, 2015, we've detected hundreds of these systems, and people are analyzing the data. The instrument, the LIGO instrument, which is the Laser Interferometer Gravitational Wave Observatory. There are a couple we'll discuss in detail in a minute what they're all about here. But people are going back, reanalyzing the data. They shut down for a period of time as they upgrade the equipment, make it even more sensitive, then start observing for a while and to release that data. People have been analyzing the data, and this one of the systems that picked out the merging of these two black holes is what was detected in 2023. And by looking at the actual shape of the wave, the gravitational wave that gets detected, you can put constraints on, number one, what were the masses of the two black holes? What was the mass of the final black hole that was created? And not so much a tight constraint, but what is roughly the distance to the system of these two binary black holes. So this one that caught the news recently, this gravitational wave source, as far as we can tell, consists of two black holes, one of about 137 solar mass, the other one of about 103, as you see here in this sort of advertisement poster.
So I'm going to point out that's 240.
That's 240. And the mass of the final product is estimated to be about 225 solar masses. So if you do the sum, you'll find out there's 15 solar masses missing. That 15 solar mass was converted into energy of the gravitational waves.
Right. That's
Now,
just...
Einstein
wow.
tells us that you can think of energy and mass as being equivalent, E equals mc squared, arguably probably the most famous equation of all of physics, at least for science nerds like us.
All right.
And so you can think of mass then as being equivalent to energy. So if you think of the amount of energy then that's needed to generate these gravitational waves, that's 15 solar masses, and you multiply that number by the square of the speed of light, you get a huge amount of energy that's being consumed into generating these gravitational waves. So really it tells you that space is really stiff. It takes a lot of energy to shake it.
Yeah.
A lot of energy.
And I will point out, too, that that's why it's so hard to detect these. That's 15 solar masses, but it's spread out over a sphere 2 to 13 billion light years across. So these waves are not that big in amplitude by the time they get here.
And like I said, the uncertainty in the distance is not well constrained, the distance. So it's estimated between anywhere from 2 to 13 billion light years away.
Right.
Which is...
So... I'm guessing this is not one where they found an optical flash event.
No, it wasn't reported as an EM signature that goes with it at all. So this is one that was just, we wouldn't even known this happened if it wasn't for the fact that it released the gravitational waves and we had our instruments running at the time to be able to detect it. Yeah. But here's the other thing to think of, which is interesting. The mass of the black hole, let's look at the most massive one, 137 solar masses. How do you get that? How do you
That's
get a
good
black
question.
hole that's so massive? You could think of number one, which is suggested here, is that maybe this is the sort of the middle panel that you see on the bottom is this labeled hierarchical origin story question mark. That maybe you had two binary black holes that merged together to form a more massive one, and you had the same situation that created the other black hole, and then those two merged together.
Right. That or I would have to speculate that these were from Pop 1 stars.
Oh, you're thinking about population 3.
Pop 3. Yeah.
Yeah.
Sorry.
That's the other aspect is maybe these were created, and maybe when you're up such a high mass, you don't even get typically as far as we know, a type 2 supernova. They directly collapse into a black hole.
Yeah.
And so the progenitor, what collapsed to form this black hole, if it indeed was a 137 solar mass black hole, it might have been a 150 solar mass star.
Right. Because there's a lot of energy that goes off even in direct collapse.
Yeah, and if it's a Pop 3 star, which means a first generation star has essentially no metals.
No metals.
Made up essentially of primordium with hydrogen and some helium, that this wouldn't last very long.
All right.
In terms of fusion,
just
right?
maybe a million years.
Yeah, maybe. So this would have collapsed, pretty rapidly after it reached the main sequence, and then left. Everything is accelerated the phases of its life compared to what we're more used to stars. But it's a great mystery. Where's the origin of these? Are they from binary merged black holes, or did they come from stars? Now, the most massive star, and there was a report that just came out today, I noticed.
Okay.
And people are reporting that one of the most massive stars they observed is on the order of about 90 solar masses, an O-type star. So that's not even close to making this black hole, you see?
Because a colleague of mine at Georgia State was working on this star, Eta Carina. For a while, it was thought to be the most massive star at about 110 solar masses. And that's theoretically on the limit of what can be done nowadays with the high metal content. But they've since found out that it's a binary, one with about 80 solar masses, one about 40.
I mean, I remember hearing that a lot, right? People speculate, this star is like 250 solar mass, it's the record. And then you get high resolution images taken from space or something, and it's a group of stars.
It's a bunch of stars.
Yeah, a little cluster association. It's like, no, the individual masses are well under 100.
Right.
So, and the problem is we don't, from a theoretical, here's how it works. You can ask, what is the least massive star you could form?
And
least
that's
amount of material.
relatively easy
and we know that from theory.
Right.
Because you know what is the amount of mass that's required to allow the core temperature to reach 10 million K or above to have sustained nuclear fusion of hydrogen and helium. And that's 8% of the sun's mass, 0.08 solar masses. So from theory, that's well constrained. The upper limit, what is the most massive star that you can form? Well, we don't know.
Right.
We can speculate, and it's like this. If you have a really massive star that's trying to form, because of its high mass, it's producing a tremendous amount of light. It has a high luminosity, as we would say. And that light carries momentum. It has a pressure. So it can push material, when a star is trying to form, it can push material away from itself. It's like trying to fill up a glass full of water. How much water can you get in a glass? Well, till it's full. I could keep pouring water into it, but it's just going to spill over the side. And it's not going to increase in volume any more than the size of the glass itself. Same as this. You could try to throw more matter on top of the star, but the radiation pressure, which is
going to blow off.
It's going to push all that matter.
Yep.
And so there is a sort of a cutoff on what is the mass of that star, which would depend on a lot of things. The metallicity of the material, because that determines the interaction of light with the matter itself in terms of number of electrons, Thomson scattering,
it heats because
all of that
of
stuff,
the absorption.
How much it's spinning, angular momentum is an issue. Even if some stars have very strong magnetic fields, that's, I'm sure, would play a role in all of this. So we don't quite know. So then how do you determine which is the most massive star? We go out and observe and look for the most massive one and say, hey, Mother Nature formed this guy. He's 100 solar masses. So do you find any that's more massive than that? If the answer is no, and you look carefully enough, then that must be the limit. Right. That's the kind of thing. So to get an extreme black hole of, let's say, 137 solar masses, then
would have taken about 150 solar mass
yeah,
star.
exactly. And
Yeah.
so it's amazing when you think, but we don't see any of those.
I'm going to ask if you want to answer this question now, or do you want to wait till
Yo, go
another
ahead.
show? Because Charles Moon has asked, could we be in a black hole? How would merging black holes affect us if we are?
Yeah, I mean, people speculate that the universe could be inside of a black hole. It's hard to tell.
It's hard to tell. There are some observations that have been looked for that have not been found to be true.
And if we were to
There's
merge,
no preferred
yeah,
rotation to the galaxies and things like that.
and if we were to merge with another black hole, then I would speculate that that would be like two universes, I should say, it would be merging or
Yeah.
touch. Think of like multiverse type of situation, and that would have probably some effect on the CMB, and people have looked for that effect.
Right.
Some people have claimed that they've seen artifacts in the CMB measurements, the leftover heat from the Big Bang, that's consistent with that. Others say no, it's not there. There's statistical fluctuation. So as far as we can tell, it doesn't look like it, but you can't never say never on this
Right.
question.
Absolutely with this
So-
question, because if I'm not mistaken, GR even does say that we have an event horizon around us.
Yeah.
There's a certain limit to what we can see and observe.
Yeah. So
So-
we don't know 100% for sure. In fact, the biggest thing, as Robert alluded to, is how do you test it?
How do you test
What
it?
are the observations? Tell me the observations that need to be done to prove yes or no on a question like that. And that's
Right.
the point, right, in all of this. And then the final slide for today
Oh,
is
okay.
actually looking at, no, the one before that, sorry.
The one before that?
Yeah, we'll do
Okay.
this one because we're running out of time.
Yeah.
Is an image of the gravitational wave detectors. So here's two of them. There are more than this. There's some in Europe. There's one in Japan. Even India is building one. So we're going to have.
And in fact, that's how we know we got a detection of a gravitational
That's what I was
wave,
gonna
is
say.
It's not relying on one detector.
Right. It's like the first one that was detected in 2015. It went off in Louisiana, Livingston, Louisiana first. And then a fraction of a nanosecond later, it went off in Washington State at the Hanford facility. And you know that the gravitational wave then passed through the Earth. There's nothing to stop them. So the direction of the incoming gravitational wave just happened to be such that it would set off the one in Louisiana first, and then in Washington State a
And
little
then
later.
the waveform was the same. And
Yeah, so you can tell
all
it.
of this
Yeah,
type
and
of
you can
stuff.
measure if they travel at the speed of light. How long will it take to go from Louisiana? And you can calculate that very precisely, and that's exactly the time delay
Yep.
in the arrival of the signals by the detectors.
It's a lot of brilliant
And they're
work.
all timed up with the atomic clock, so we know, they're all synced up and stuff, so we know when they arrive. Yeah, so it's definitely very interesting. Maybe in the future we'll do a podcast in detail of looking to see how these gravitational wave detectors actually can detect
What they do.
the signature. So it's a very amazing. I mean, it's really amazing when you think about it. Okay, well, we run out of time for today. If you're interested in these kind of things like gravitational waves, whether or not we live inside of a black hole.
Yeah, it's a good question, Charles.
Yeah, and one of the things you like to do, of course, is to gain knowledge by going into different fields, whether it's STEM fields or humanities. We need people in everything to write about this stuff,
Right.
to try to communicate to the general public more of what physicists and astronomers and astrophysicists study. There's a lot of interesting stuff, but you don't really appreciate till you know the little bit of the foundation behind it. You don't need to
Absolutely.
be an expert, but you can appreciate it with just a little understanding and a little bit
Yeah.
of description, and you can be amazed of what's out there.
Yeah. I mean, I once told students, hey, I don't necessarily want to turn you into astronomers. There's not that many jobs for me.
Yeah.
But you know what? You can think this stuff is cool and contact your Congress critters.
All right, that's it. So one way you can learn stuff, of course, is go to universities like UND.
Absolutely.
We have both online classes and also on-campus courses, and things are going to be starting up here in a little over a month from now.
A little month of them
We get
now.
a little busy, and which is a great thing. There'll be lots of people around, and we're going to have one of the highest enrollments, I think, ever coming up this fall.
Oh, wow.
So that's going to be really exciting.
That's going to be exciting.
Yeah, and if you happen to be in the area, of course, drop by to see Robert and I. We'll
Absolutely.
definitely talk to you, show you around, show you the podcast room,
Absolutely. Well, I don't know about that.
show you the broom closet.
So your room closet. Yeah. Yeah.
Now, the next podcast will happen a week from today, so that's on July the 29th at 5 p.m. Central Daylight Time. And we always leave you with a quote at the end of our podcast. So today I decided to select, since we talked about the Parker Solar Probe,
Okay.
a quote from Eugene Parker.
Eugene Parker.
Now,
Okay.
he lived from 1927 to 2022, so he was in his 90s.
Mm-hmm.
And he was alive at the time when they launched the Parker Solar Probe and named it after him by NASA.
Oh, that's
he was
not,
able to.
that's not normal.
Yeah,
That's
he was
great.
able to
That's
appreciate
awesome.
that. Unfortunately, he wasn't around for this close approach data that
Yeah.
came in back in December. And Parker, if you want to, do you want to explain a little bit what Eugene Parker is known for in this context?
I actually don't remember.
Remember the solar wind?
Is he the one that speculated first that
Yeah.
the solar wind?
Yes.
Yes, then I know his story because he was laughed at.
Yes.
Literally laughed at when he proposed the solar wind because the sun, of course, has enough mass that the escape velocity is such nothing could ever move that fast. And no particle with mass could. Anyway.
Yeah.
And so it was just laughed at. And people were telling him, well, people have been wrong before. I know your math supports it, but people have been wrong before. And he took it and said, we'll see who's wrong.
Yeah.
And so then the Skylab went up with instruments that looked for this hypothesized solar wind just to prove it wasn't there was the plan, except it was there.
Yeah.
So, yeah, this guy is one of those who he definitely got the last laugh.
Yeah, and that whole idea of the solar wind and the properties of the sun is well established now in solar
Right.
physics. So the quote is from Eugene Parker, and here's the quote, and it ties right into what Robert said. If you do something new or innovative, expect trouble.
Mm-hmm.
But think critically about it, because if you're wrong, you want to be the first one to know that.
Absolutely.
Thank you very much for watching. Please remember to give us a thumbs up, subscribe if you haven't subscribed, and we'll see you next time. Thank you.
See you next time, folks.